This is the video lesson for Ohm's Law with combination circuits. The learning target for this lesson is, I am learning to use Ohm's Law to solve real-life problems involving combination circuits. The success criteria for this lesson are, I can calculate the equivalent resistance for the entire combination circuit. I can calculate the current for the entire combination circuit using Ohm's Law. I can calculate the current for each parallel branch of the circuit using Ohm's Law. And I can calculate the voltage drop for each resistor in the circuit using Ohm's Law. So what is a combination circuit? A combination circuit is a circuit with both series and parallel components. The current in a combination circuit is determined based on the different parts of the circuit. For the series parts, the current is constant, and for the parallel parts, the current is split across the branches. So the current is different for each branch, potentially. The voltage drop is determined based on the different parts of the circuit. So depending on whether we're talking about the series part or the parallel parts of the circuit, the voltage drop is going to be determined by those parts. So for a series part, we use Ohm's Law to calculate the voltage drop. And for the parallel parts of the circuit, the voltage is the same across each branch. So let's look at determining the equivalent resistance in a combination circuit. So we're going to follow these steps to find the equivalent resistance. So first, we're going to find the equivalent resistance for the parallel components of the circuit. So here on this circuit, this sample circuit, we have two branches. So we have branch C to F and branch D to E. So remember that to find the equivalent resistance for parallel components, we do 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, etc. So 1 over the equivalent resistance is equal to 1 over 15 plus 1 over 10. So that's equal to 0.167. So then the equivalent resistance is equal to 1 over 0.167, which is equal to 6 ohms. So the equivalent resistance for the parallel parts of this circuit is 6 ohms. So add that resistance to the resistors in series in the circuit. So that's the next part. So to do resistance in series, we just add the resistors one after the other. So we have the light bulb is in series. So we have equivalent resistance is equal to 10 ohms plus 6 ohms. So our equivalent resistance for this whole circuit is 16 ohms. Now let's look at determining the current in a combination circuit. So you're going to determine the total current in the circuit using the equivalent resistance and the voltage. So for the series components in the circuit, this is going to be the total current that we use. For the parallel components, the sum of the current inside each branch is equal to the current outside the branches. So just like with a parallel circuit, so the total current is equal to the current in branch 1 plus the current in branch 2 plus the current in branch 3. But before we can figure out the current across the branches, we've got to do something first. So our equivalent resistance that we calculated in the last slide is 16 ohms. So to figure out the voltage drop across the entire circuit, we're going to use Ohm's Law, I is equal to delta V over R. So the current across the entire circuit is going to be 16 volts divided by 16 ohms, which gives us a current of 1 amp. And that's for the entire circuit. All right, so before we can figure out the current in the parallel branches, we've got to first determine Ohm's law. We've got to first use Ohm's law to determine the voltage drop. So we're going to determine the voltage drop across the series components using Ohm's law. So we're going to use delta V equals I times R. So the source voltage, the battery or whatever the source voltage is, minus the voltage drop across the series components is going to equal the voltage available for the parallel branches. So we'll do an example. We'll work on this example in just a second. So the remainder of this calculation that we did above is going to be the voltage used to calculate the current in each parallel branch using Ohm's law. Okay, so we know our current across the entire circuit is equal to 1 amp. So we can figure out the voltage drop across the light bulb by using delta V equals IR. So delta V across the light bulb, across points A and B, is equal to 1 amp times 10 ohms. So that is going to be 10 volts. So that leaves us with 6 volts spread across the parallel branches. So we have 6 volts across this branch and 6 volts across this branch. So now that we have the voltage that is shared among the two branches, we can go back and determine the current across those branches. Okay, now that we know the voltage across the branches, we can figure out the current. So now that we know the voltage drop from the series components, we can calculate the current for each parallel branch. So we're going to use I equals delta V over R. So if we figure out the current for C to F, that's going to equal delta V. So in this case, we're looking for C to F. We're talking about 6 volts divided by the resistance, which is 15 ohms, which is going to be a current of 0.4 amps. And the current across DE is 6 volts divided by 10 ohms, which is equal to 0.6 amps. And if we look at our equation here, I total, so the total current across our branches should equal the sum of the individual currents. So we have 0.4 plus 0.6, which is equal to 1 amp, which is the total current that we know for the circuit. So we've got that figured out. So we now know all the important information about this circuit. All right, now we're going to put it all together and figure out all of this information for this new example. So first thing we're going to do is figure out our equivalent resistance. So first we're going to figure out the equivalent resistance for the parallel branches. So we have, so here notice we have 2 resistors in series. So we have this bulb with the 10 ohms and this resistor number 2 with 5 ohms. So since these are in series, we're just going to add these together. So the total resistance for this branch is 15 ohms. So our equivalent resistance over the parallel branches is equal to 1 over 15 plus 1 over 15 plus 1 over 10, which is equal to 0.233. So equivalent resistance for the parallel branches is equal to 1 divided by 0.233, which is equal to 4.29 ohms. So we'll add that plus the current, or plus the resistance from bulb 1. So that's 10 ohms, and we end up with 14.29 ohms for the equivalent resistance. So we'll put that in here, 14.29 ohms. So now we'll figure out the current for the entire circuit. So we have current is equal to our voltage, so that's 18 volts, divided by the total resistance for the entire circuit, so that's 14.29. So that current is equal to 1.26 amps. So we'll write that down here, 1.26 amps. So we can figure out now the voltage drop across bulb 1. So delta V is equal to 1.26 amps times 10 ohms. So that gives us a voltage drop of 12.6 volts. So we'll put that in this spot right here, 12.6 volts. Now, we need to figure out how much voltage we have for each branch of this circuit. So we have 18 volts minus 12.6 volts, which gives us a remainder voltage of 5.4 volts. So each branch of this, of the parallel branches, has a voltage available of 5.4 volts, and they all share that voltage. So now we can determine the current across each branch. So current is voltage divided by ohms, resistance. So we have, for the first branch, we have 5.4 divided by 15, which gives us a current of 0.36 amps. So that's going to be the current at resistor 1. So that's 0.36 amps. The current at bulb 1 is the current for the entire circuit. So that's 1.26 amps.
All right, now we'll calculate the current for the second branch. The second branch has the same voltage, 5.4 volts, and it has a combined resistance of 15 ohms. We have resistor 2 with 5 ohms and resistor 3, the second bulb, with 10 ohms. So add those together and you have 15 ohms. And so we have a combined current for the second branch of 0.36 amps. So resistor 2 has 3.6 amps, 0.36 amps, and the bulb 2 has 0.36 amps. And finally, we're going to figure out the current for resistor 3. So the voltage is 5.4 volts. The resistance is 10 ohms, which gives us a current of 0.54 amps. All right, now to double check, we can add all of our resistance across our branches and figure out if that totals the total resistance for the circuit. So 0.36 plus 0.36 for the second branch plus 0.54 for the third branch. Add all those up together, and that equals 1.26 amps, which is what we should have. All right, now we can figure out our voltage drops across our 3 branches. So the voltage drop across resistor 1 is 5.4 volts. The same thing with resistor 3, 5.4 volts. Okay, so across resistor 2 and across bulb 2, since these are in series, we got to actually calculate the voltage drop. Remember that in parallel circuits, the voltage is the same across any of the branches. So to figure out the voltage drop across resistor 2, and do delta V R2 is equal to our current, which in this case is 0.36 times our resistance, which is 5 ohms. That gives us a voltage drop of 1.8 volts. Okay. Then for voltage drop across bulb 2, it's going to be the same current because the current in a series circuit is the same everywhere, times 10 ohms. That's going to give us a voltage of 3.6 volts. Now if we add these two together, 1.8 volts plus 3.6 volts, it equals 5.4 volts, which is the voltage across the entire branch. So we've got all of our values in our table. So we figured out all of the important numbers that we can with this particular circuit. So we've done a great work. We've done a great job, and we now know how to calculate all of the information for a combination circuit. All right, everybody, go out there and keep asking questions. It's how you learn new things.